Hi there everyone, in this last video on continuous random variables we are going to be looking at the cumulative distribution function, also known as a CDF. So this is the sixth and last video that we're going to be dealing with. For a continuous random variable, the cumulative distribution function is the function that tells us the probability up to and including a certain value. So of course we know that we can get the area underneath these curves using integration. So here's the formula here. It is just cumulative density function is cumulative distribution function is just given by the integral of the function from x down to a, where a is our starting value in our function, up to a certain value of x. So the area up to and including x. That's the formula for a CDF. If we look at this example here, it's talking about cumulative frequency. So going back to data again, something that we know. Here we've got some data about the ages of teachers on the staff of a school. And we can see we've got 14 teachers between 20 and 30 years old, then 31 teachers between 30 and 40. So what we could say is that the number of teachers up to and including those who are 40 years old is 45 teachers. So the cumulative frequency up to including 40 is 45, just the sum of those two frequencies. Similarly, we can go down and say up to and including all those teachers who are 50, we've now got 30, 40, 50, 57, 58 teachers. Okay? So if we look at the table here, you can see these values here, which is the cumulative frequency, sort of the running total as we go along. We can then graph these cumulative frequencies on a graph like this, and we can work out medians and lower and upper quartiles. So this is called the cumulative frequency graph. It's called an ogive as well. And you can see it's always going up. It can never go down again because we're always adding on frequencies as we go along. So that's the idea from if we're looking at data. So let's imagine that this was a cumulative distribution function here. And what you'd be looking at is that this here would be 1 because the probability has got to end up being 1 at the end of the distribution. So the total area under the curve is 1, which means we're going to finish up being 1 here at the end of the interval. So let's say this is 6 and this is 0 here. So what this is telling us is that as we go along here, let's take this value here at 3, this is the up to and including a value of 3. So let's say that that is 0.8. Okay, so if we wanted to work out what's the probability that we get between 3 and 4, what we'd do is we'd work out the probability we were at 4 and then minus off the probability that we were at 3. So the answer to that would be 0.1, the chance that we were between 3 and 4. And you can see that in the formula up here. The chance we're between two values is we work out the cumulative distribution function at D, in this case 4, the cumulative distribution function at 3, and then just subtract those two. So let's look at 3 examples here. The first one, we've got our uniform continuous distribution function, and we want to work out what's the cumulative distribution function. So as it's got at the top here, the cumulative function will be such that f of k gives the probability that x will take values less than or equal to k. Okay, so 6 is here, 1 is here. So clearly, the cumulative distribution function starts at 0 at 1. Okay, 2, 3, 4, 5. We know we're going to end up at 1 for 6. That's our final value there. Okay, so like I said, at 2, what's the probability for the cumulative function that we're less than or equal to 2? That is the area between 2 and 1. So that is going to be 0.2. Let's just get this here, that's 0.5, 4, 0.3, 0.2, 0.1, 0.6, 0.7, 0.8, 0.9. So there we are at 0.2. What's the probability that we're less than or equal to 3? See, that is going to be 0.4. Less than or equal to 4. 1, 2, 3 times 0.2, that's going to be 0.6. Less than or equal to 5 is going to be 0.8. And there we go there. So I've just evaluated particular values, but that is going to be a continuous function there. So it's going to come along here up to 0, and then from there it's going to go straight across there, 1 from then on. So we could work out the equation of that line. Let me show you the more formal integration way that you can work out what that function is. So the cumulative distribution function, I'll call it a big f of x. I know here they've called it little f of x. I'm going to call it big f of x in everything that I do here. It's just the integral x to, in this case, 1 of f of x dx. Okay, and I know it's strange to have that x there. That looks really weird, so what I like to do is just put a k there to start with and say that f of k. So that is the cumulative distribution from k downwards, where k is an x value. So if we do that integration, we get 0.2x between k and 1. So 0.2k minus 0.2 times 1, 0.2. So there we go. Our cumulative distribution function will actually look like this. 0.2x minus 0.2, and that's the equation of this line that you see here. So more formally, to define it all, so that's just from there on. Let's get it really formal here. So we'd say f of x is equal to, there's 3 sections here, 0 for x values less than 1, 0.2x minus 0.2 for x values between 1 and 6, and it's going to be 1 for x values greater than 6. Now notice here I could have changed these two around if I wanted to and made that one there less than or equal to and this one here just less than. It doesn't really matter there because it's a continuous function. It doesn't matter. So that is the formal definition of the cumulative function for this one. So there's 3 parts to this function here that we're looking at. First of all, the function is up to and including 1 is equal to 0. Then we get 0.2x minus 1 for values between 1 and 6. And then it's 1 from then on. So there's what that cumulative distribution function looks like. Note here that we're looking at the probability up to and including a certain value. So if you look at x equals 5, it looks like we're across there at 0.8 on the axis there. So the probability that we're 5 or less is 0.8. The probability that we're, let's say, 3 or less is 0.4. So the chance that we're between 3 and 5 in this function here is 0.8 minus 0.4, which is 0.4. Second example here, a little bit trickier here because the probability density function isn't just a flat line here, it's sloping up. So let's go straight to the second method I used in the last one. Big f of x is just the integral from k to 1, remember that's just the lowest point there, of this function, 2x minus 1 dx. That's all it is. The area under this curve from a certain x value down to the start. So if we do the integration there, 2x minus 1, we could think of this as the reverse chain rule. So add 1 to the power, divide by the new number, and those 2's will cancel. So we're really just left with x minus 1 squared between k and 1. Alright, so this is k minus 1 squared minus 1 squared. So k minus 1 squared, because that's 0 there. So let's formally define f of x for all our x values. Again, it's going to be in 3 parts. It's going to be 0 for x values less than 1. It's going to be x minus 1 squared for x values between 1 and 2. Okay, that's the limits of this function here, 1 and 2. And then it's going to be 1 for x values bigger than 2. Okay, there's the definition for that one. 3 parts to this one here. So we're up to 1, we're equal to 0. Then we've got x minus 1 squared between 1 and 2. Let's stretch that out a little bit. And then, of course, from then on, we're equal to 1. So there's the cumulative distribution function for this one here. And the third one here, this is this exponential function that we dealt with before, a really similar one. The CDF, the cumulative distribution function here, the integral from k to 0. In this case, this is going to x equals 0. And this one's a little bit strange because it keeps going off to infinity, but it'll work out of 0.5 e to the minus 0.5x. So let's do this integration. I'll put the 0.5 out the front, and I'd say that e to the negative 0.5x, 1 over negative 0.5 e to the negative 0.5x. The reverse chain rule there, between k and 0. Okay, so 1 over negative a half is the same as negative 2 times that. So this is negative 2 times 0.5, which is just negative 1. So negative e to the negative 0.5 x between k and 0, which is negative e to the negative 0.5k minus negative e to the negative 0.5 times 0. You've got to be really careful here because a lot of the times when we substitute 0 into these integrals, we get 0. But of course, in this case here, we don't. This is e to the power of 0, which is 1. Okay, so this thing here is equal to 1. So you just got to be really careful there when you do this. So I get negative and negative is plus. So we end up with 1 minus e to the negative 0.5k. So let's formally define in the 3 parts what this will look like. So f of x is equal to, first of all, it's going to be 0 for x values less than or equal to 0, or less than 0, it doesn't matter. It's going to be 1 minus e to the negative 0.5x for x values greater than 0. Now, let's have a look at the graph of what this looks like so we can get a feel for the fact that this actually heads off towards 1 at the end there. So here's the first part. The graph is 0 up to including 0, and then it's 1 minus e to the negative 0.5x for x values greater than 0. So you can see it heads off and gets closer and closer to 1 as x tends towards infinity there. So that's the cumulative distribution function, what that looks like for that one.